Hello. Today we're going to prove that the divergence of a curl is 0 and the curl of a gradient is 0. So let's start with the first one. A is a vector. A is going to have components of A1, A2, A3. Okay? The upside delta symbol is the del operator, or the del vector, which simply has components of partial derivatives, d by dx, d by dy, and d by dz. Okay? So using that, we can work out the curl for our first formula. So the curl, we construct our usual table, I, J, and K. The components of our del operator are our partial derivatives. The components of our A vector are A1, A2, A3. Okay, you should be familiar with the cross product. In this case, it's called the curl, if we're involving the del operator. So we take these sub-determinants, cover up the I column, we then get, just to make things clear, this is the curl. So we get the partial derivative of A3 with respect to y minus the partial derivative of A2 with respect to z times I. Now we minus, cover up the j column, we minus partial derivative of A3 with respect to x minus the partial derivative of A1 with respect to z, okay, times j. Okay, and finally we cover up the k column. We add the partial derivative of A2 with respect to x minus the partial derivative of A1 with respect to y times k. So I hope you understood that. If not, please watch my videos on the cross product and the curl. Right, so that's the curl, but remember, we have to take the divergence in order for it to come 0. So how do we take the divergence of this? Well, the divergence is simply the dot product. So we simply have to, for our I, j, and k component, for our I component, we take the partial derivative with respect to x, because remember, the components of our del operator were d by dx, d by dy, d by dz. So the divergence is simply going to be the partial derivative of this term with respect to x minus the partial derivative of this term with respect to y plus the partial derivative of z of this term. Okay, x, y, and z. So let's do that then. Okay. Right, so again, we have therefore d2 a3 dy by dx minus d2 a2 dz by dx. Multiply that by I. Okay, we're simply just taking divergence now. Therefore we get our second order mixed partial derivatives. Then we minus d2a3 dx by dy minus d2a1 dz by dy times our unit vector k, which I can't really get there, but anyway, that's our unit vector k timesing this term. And finally we add d2az dx dz minus d2a1 dy dz. Okay, so all we did is we simply differentiated each component with respect to x, y, and z. This component with respect to x, that component with respect to y, that component with respect to z. And so therefore we got mixed partial derivatives. And that is the divergence of the curl. Now this should equal 0. Does it? Let's just try. Now we know the rule for mixed partial derivatives. It doesn't matter which order the differentials are, they still bring about the same partial derivative, as long as a3 stays constant, for instance. So therefore, they should cancel. This mixed partial derivative should cancel with that one. xy, y, x. It doesn't matter which order they go in. They cancel because that's a minus. And similarly, a2, we have xz, zx. They cancel. And then finally, we have, oh, remember that minus makes that a plus inside. So that actually becomes a plus. So therefore, our a1s cancel, giving us 0. Okay? So therefore, the divergence of a curl of a vector field is 0. Now finally, we're going to look at our last theorem, and it's the curl of a scalar field, then, well, yeah, the curl of a gradient of the scalar field, I should say, okay? Like so, okay? So, remember that the components of our del operator are partial derivatives, so therefore we're simply taking the partial derivative of our scalar field. Phi, remember, is just a scalar field. It can have components x, y, z. So therefore, del phi is simply going to be equal to d phi by dx plus d phi by dy plus d phi by dz. Okay? Now we take the curl of this with the del operator. So we're going to make our table again. I, j, k. Okay? Components of our del operator are partial derivatives. D by dx, d by dy, d by dz. Components of our gradient field is simply partial of phi with respect to x, partial of phi with respect to y, partial of phi with respect to z. Okay, just from that term here. Now we can compute the curl of our gradient. Again, we do the subdeterminants. We take the partial derivative, so it's going to be a mixed second order partial derivative, so we're going to get d2 phi dz by dy. Okay, that times that minus that times that. When we times partial derivatives, we're literally taking the partial derivative of one another. And similarly, we're going to get d phi by dy by dz. Oh, and of course we times our x unit vector I. Okay, they seem to be quite interesting. We have, like we saw before, it doesn't matter which way they are, so they should cancel. But we'll just carry on and see what we get. We're going to minus, cover up our j component, minus d2 phi dz dx minus d2 phi dx dz times our j component. Okay? Then finally we add our z component, our k component. Correct the k, so therefore we get d2 phi dy by dx minus d2 phi dx by dy times k. Alright, so like we saw before, it doesn't matter which way the mixed partial derivatives are at the denominators, z and y, y and z, doesn't matter which order, they bring about the same partial derivative. So therefore, that cancels, and that cancels to become our 0 vector. Okay, just 0. So there you have it. I didn't have much time today, so sorry if that was rushed, but I hope you understood what I was doing there. So we proved that the curl of a gradient field is 0, and we proved that the divergence of a curl of a vector field is 0. See you in the next video.